Can everyone see my screen?
Yes.
Hi.
All right. So next speaker is Stav. Please take it away.
Okay. Hi. So thank you to the organizers for giving me the chance to present my work. And this work was done with Professor Huang Li. So most of the introduction has already been given, but I'll probably just for completeness, I will also talk about phase sensitivity and so on a little bit. But the idea here is to think about a LIDAR, and a LIDAR is basically a sort of light-based version of a radar, where you are trying to find distance and ranges, even velocities using laser sources or coherent light, or even other quantum sources of light. The exact setup that I'll be talking about is a Michelson type interferometer. It's basically the same. It's a Michelson interferometer that is being used as a LIDAR, and then we'll try to see how you can get the best phase sensitivity out of it. So yeah, as Dr. Lee said, every graduate student here has to draw his own interferometer once. I did it recently, so this is my interferometer. So you have this source which will give you either coherent or squeezed or any kind of input. You have the basic Michelson interferometer setup, which is just a single beam splitter, and then sort of two mirrors at the end here are now replaced by, in one arm you have the target, which is the arm basically not under your control, and this is the arm in which you are trying to calculate the acquired phase, the extra relative phase, and the other arm is the reference arm, and it goes through a delay line, it comes back, goes through the beam splitter again, and then you detect the number of photons using photon detectors at the end. So this is just a sort of relabeling of the Michelson interferometer to use it as a LIDAR. And you can also consider, and we'll talk about this, some noise in the arm, which is sort of a realistic assumption. So this phi, that is the acquired phase, basically tells you what is the range of the object. So that's why the term LIDAR. So again, although Dr. Lee talked about this in detail, just a quick review of that. You have, in the quantum case, you will have the errors in the phase measurement because of the number of photons that are received at the two detectors will fluctuate. The quantum fluctuations in the photon numbers, and therefore the photon number difference, which is this J3, will also fluctuate, and that gives you error. There is also the radiation pressure error, which was also talked about. But if the input power is not very high, then that error and can be mostly neglected. Also, if the target object and the mirrors are very heavy, then that error can be neglected. So the sensitivity, phase sensitivity, is basically measured by the variance in the measurement of the phase phi, and in this specific case, you are doing it using the photon number difference between the two detectors, and therefore the operator in question is under consideration is J3, and therefore the variance of J3 by the derivative of J3 with phi. So there are two kind of fundamental limits to this. If you did a sort of classical version of this experiment, then the usual statistical limit applies to your phase sensitivity, and that's this short noise limit, which is 1 by the square root of the average number of photons that you are inputting into the system. It's almost like saying that if you do n trials of the experiment, then the statistical error, the standard deviation is proportional to 1 by root n. Whereas in quantum mechanics, the amplitude and the phase are complementary variables, and therefore, if you look at the Heisenberg uncertainty limit, then you get sort of delta n times delta phi is proportional to 1, and therefore that Heisenberg limit to the phase sensitivity is a sort of more higher scaling limit of 1 by n. So what happens if we use a coherent input source? So I start with a sort of simple example, and Dr. Lee also, I think, talked about this. So you use a sort of classical source, which is a normal coherent laser as your input into the LIDAR, and then you try to see what kind of phase sensitivities that you can achieve, what are the levels of phase sensitivity that you can achieve, and also what is the effect of noise on that. So again, a coherent source is sort of ground state of the harmonic oscillators given some extra number of photons, mean number of photons, so it gets sort of shifted by that amount. So a sort of brief snippet of how the calculation is done and what are the operators involved. So you start with this vacuum mode from the two input sides, and then you apply the basic the different operators that act on that input. So you first sort of coherentify the input in one mode, and the other mode you sort of keep vacuum. Then you apply the first beam splitter, there's the phase shift, and then there's the loss beam splitter. So the loss here is sort of modeled by a beam splitter with a certain transmissivity, which sort of makes sense in the sense that you get a certain number of input photons, and depending on the transmissivity, only a certain amount of photons reach out. But additionally, sort of the quantum effect of that noise addition is that because you also have the vacuum coming in from the other end of the loss beam splitter, you also have some extra fluctuations because of the noise. So that is this beam splitter. The loss transformation, which is like the eta is the transmissivity, and RL is just 1 minus eta square root of that. And then you have again the same beam splitter acting on the state, because you have to go back to the detectors. So once you do that, you sort of have all the ingredients to calculate the expectation of J3, the variance in J3, and so on. So you can calculate the phase sensitivity. So one sort of slight diversion from the kind of routine way of doing this is say that you assume that you want to control the number of number of photons that go into each arm. So the idea, the sort of intuition there is that because you are losing photons in one of the arms, which is like your target arm, and you are not losing photons in the other arm, which is your reference arm, you would want to lose less number of photons and still maintain your phase sensitivity. So you would want to control how many photons go into one arm and the other, and then see what sort of distribution gives you the best phase sensitivity. So then what you can essentially do is change the first beam splitter from the usual 50-50 configuration to a more sort of general TR configuration, and see what your expression for the phase sensitivity is. And ultimately, it turns out that you find that the best case scenario is still the 50-50 beam splitter. So even in the case of the noise, you still want the beam splitter to be 50-50, and that gives you the best phase sensitivity. So on the plot, in the plot on the right, you can actually see that irrespective of the noise level, so eta small means large noise, so you sort of lose 1.2 means you lose almost 1/5 of the photons in the top arm, and eta 1 means no noise. So you can see that irrespective of the levels of the noise, the phase sensitivity is always minimized at the beam splitter transmissivity of 50%. So the 50-50 beam splitter is always the best. Another thing that you sort of immediately see is that the phase sensitivity, even the minimum value, sort of grows linearly with the levels of the noise, and you can see in this expression, delta phi is sort of falls linearly with eta, and eta great being less than 1, you sort of lose precision linearly with eta as you increase the noise. With the coherent sort of classical source, you can never beat the short noise limit, because these are all ratios with the short noise limit of 1 by alpha, and you see that the best that you can do is short noise limited. So the sort of two lessons from here are that noise will lead to reduction in your phase sensitivity, and also that the 50-50 beam splitter is still the best. So now we sort of move to a more complicated situation. So instead of using a simple coherent classical source, we could also use squeezed light as one of the inputs. And the general idea there is that because along one of the quadratures you have lesser uncertainty, that somehow might help you in increasing the phase sensitivity. And as Dr. Lee already discussed, you saw that it does give you a e to the power r proportional increase in the phase sensitivity. So let me quickly move to the next one. So here I just want to sort of give a sense of the two mode squeezing, and because it's very similar to how it's done in terms of to the single mode squeezing case, but there are some essential sort of conceptual differences between the output state. So a single mode squeezed state is just sort of saying that you take a Gaussian, the usual ground state, and then you sort of squeeze one of the quadratures, quadratures by r square, and therefore the other one goes increases by r square, and that gives you a increase in the phase sensitivity. But in the two mode case, it's apart from the squeezing of the quadratures, there's also the effect of them being correlated. So you can sort of write this in the position basis, you can write these states like this, and then when you sort of squeeze when you squeeze one of the quadratures, this xa minus xb square, then you see that the variance in xa minus xb actually falls below half. So that sort of is an indication of an entangled state, that xa and xb, the positions of the two states, are correlated, or they are entangled. Sort of the extreme case gives you a better idea of that this is happening. If you take r tending to infinity, then these just go to delta functions and you get a delta xa minus xb. So xa and xb themselves are completely unknown, but the correlated operator xa minus xb is exactly known. So if you know one, you know the other, but you don't know the individual one. So this is almost exactly like the Bell state. The entropy of the total state is zero, but each of the individual states has maximal entropy. So that's why this is the sort of motivation to use a two mode squeeze light is also to use the entanglement and not just the squeezing. So so this is the basic algebra of the two mode squeeze state. You basically first take two coherent inputs. So you have two coherent states with alpha and beta number of photons, and the respective phases θ1 and θ2, and you pass them through a parametric amplifier, which is basically what does the squeezing, which applies this operator S of z on the input modes, and sort of get a linear combination of A and B out, and the scaling parameter R of the squeezing, which tells you how much squeezing you are doing. And there's also a squeezing phase associated, which is this capital phi, and you will see that, and we'll discuss that this is something which is an important parameter. So once you do this, you can calculate the average number of photons in the output, the total average number of photons in the two outputs, and you see that it's sort of, as expected, is proportional to the total coherent input that you gave, and also the squeezing sort of amplification that you did. But in terms of the phases, the important thing to notice here is that it does not depend on the individual phases θ1, θ2, and phi, which is the sort of the input parameters, these input phases, but rather on a specific combination of theta, which is of these three parameters, which is this angle capital theta, and this capital angle, this capital theta. And it's easy to see that at theta equal to pi, this n bar goes to maximum. the 2 points to notice here are that it depends only on this combination, and it goes to its maximum value at pi. So as we saw that the phase sensitivity sort of is inversely proportional to the average number of photons, you would also expect that the phase sensitivity in general in this case will also be maximized for this parameter theta being equal to pi, and that's exactly what you see, that this delta phi square also maximizes at theta equal to pi. But a small difference that you also see here is, even though the average photon number just depends on this combination, the phase sensitivity does depend on the individual angles theta 1 and theta 2. So there is some similarity in terms of where this is where this function is minimized. This delta phi is lowest at theta equal to pi, and the average number of photons are maximum at theta equal to pi, which is on expected lines. But it's also important to see that there is this slight difference of dependence on theta 1 and theta 2. So, and we can use that, and that's the idea. So so again, just to sort of see if we get what kind of benefits that we get from the two-mode squeeze state, we see that for a specific case where we choose alpha equal to beta, so the two input coherent modes are exactly the same, and the maximum sort of angle in terms of the phase sensitivity, then the short noise limit 1 by n bar is proportional to e to the power 2r, whereas the phase sensitivity delta phi square calculated from the squeeze state by the usual sort of operator algebra, the variance divided by dj 3d phi, that is proportional to e to the power 4r. So you basically get a gain of e to the power r or e to the power 2r in delta phi square, if you want to put it that way. Then delta phi square, you get a gain of e to the power 2r. So your phase sensitivity enhances by a gain factor proportional to the squeezing factor, and that's all on sort of expected trends, and you get it on the maximum. So this sort of should already settle the case that theta equal to pi, you will get the best sensitivity, but there are some points that sort of lead you to the realization that may not be the end of the story. So the average photon number just depends on the combination theta, and so does the photon number statistic. So if you just look at the probability of getting n1 photons in one of the and I mean the photon number statistics just after just after you have created this two-mode squeeze state. So if you just calculate p of getting n1 photons in this arm and n2 photons in that arm, you also see that number is also dependent only on this combination theta and not on the individual angles. And you see that the sort of the photon number statistics kind of tell you that you get this, as Dr. Lee also showed, this image of a noon kind of state, which is maximally entangled, and that gives you the best phase sensitivity, because obviously with the noon kind of state, you don't know the number of photons in the arm. It's either 0 or n, so the fluctuation in the number of photons is proportional to the number of photons, and therefore the delta phi, delta n proportional to 1 limit tells you that delta phi is 1 by n. So you can sort of hit the Heisenberg limit the best with theta equal to pi. So that's all settled. But if you see the photon number statistics just after one beam splitter, you realize that number is a linear combination of all the sort of angular momentum modes, and therefore you see that is not dependent only on theta. Because of the superposition, you see that the dependence on the individual angles theta 1, theta 2, and phi also appears. So therefore, there is this scope of optimizing this number further and doing something better. But then the idea is that if you can already beat the short noise limit, then and also sort of if theta equal to pi is the best case scenario, then why bother with that? But we'll see that that's not the case when you add noise. So now if you just a second, sorry. If you added some loss, which is this eta parameter that we had in the target arm, then things are slightly different. So Caves, when he initially sort of proposed the use of these two-mode squeeze states for various applications in interferometry, assumed that the squeezing angle phi being set to 0 can be done without any loss of generality, because the idea again there was that since the photon number statistics and the photon number also depend just on that combination theta and not on the individual angles, it doesn't matter what you choose the squeezing angle to be, you can still achieve the best phase sensitivity and sort of resolution as well. Similar results were shown in Xiaoqi and Dr. Lee and Xiaoqi's paper here and at LSU, that theta equal to pi is the best case scenario, and you can still choose pi equal to 0, even in the case with without noise and with noise. That was the assumption, and they found certain limits to the phase sensitivity. And then, as I said, that Beretella and Gary in 2015 PRA, they showed that phi equal to 0 is not the general setting. So after the beam splitter, so that sort of motivates you to optimize further. So if you choose phi equal to 0, which is the squeezing angle to be 0, and still have that sort of maximal condition that theta equal to pi, you still work under that assumption. Then in the case of a loss factor of eta, and this RL square is just 1 minus eta square, you get that your phase sensitivity as a ratio of delta phi short noise is enhanced by this factor. And then you can essentially see that this, so when you want to beat the short noise limit, you want the factor in the bracket to be greater than 1, right? And then since R is large, this number basically goes to 0 for sort of a large enough squeezing factor. So you want this to be greater than 1, which tells you that eta at most, eta square, sorry, there's a typo here, eta square can at least be 1/3. So if you have a loss of greater than 66%, sort of 2/3 loss, then you can never beat the short noise limit, even for infinite squeezing. So even if you sort of pumped infinite number of photons, you will never be able to beat the short noise limit for eta less than eta square less than 1/3. So that was the originally the previously known result with the squeezing angle set as phi, but this theta set to its sort of maximal value of pi, which was assumed to give the best phase sensitivity. So now what we tried was sort of remove this condition on phi and sort of find a general expression for the phase sensitivity, because the photon number statistics we know depends on the individual angles theta 1, theta 2, and phi. So we also found an expression of delta phi square as a function of theta 1, theta 2, and phi. And then if you looked at a sort of toned down version of that expression, just for simplicity, where you assume that the angle phi, the squeezing angle phi is non-zero, but still sort of work under the assumption that capital theta, that combination is still pi, you get a slightly different expression depending on the value of phi. And on first sight, it seems if you sort of put phi equal to 0, you get back to your original expression. But the idea here is that this factor, the limiting value can go down up to 1/2, whereas in the previous expression you saw that there was no phi dependence, and therefore this was just RL square by 2 eta square. But in this expression, this number can go down up to 1/2 for phi equal to pi by 4, and that would tell you that if you wanted phase sensitivity beyond the short noise limit, even for larger than less than 1/3 eta square, you could achieve that. But a sort of slight problem here is that if you take phi equal to pi by 4, if you take phi equal to pi by 4, then this number explodes. So you can't exactly take phi equal to pi by 4, but also sort of notice that there's this exponential factor e to the power 2r. So for a large enough r, you can go very close to phi equal to pi by 4, and still this number sort of goes almost to 0 because this number is huge. And then again, the sort of defining condition for beating the short noise limit as this expression should be greater than 1. And we know that this goes up to a half. So you actually get RL square by 4 eta square greater than 1 as your less than 1 as your sort of defining condition. And so you can go down up to eta square, and sorry again for the typo, this is eta square greater than 1/5. So now with this sort of additional freedom of choosing a non-zero squeezing angle, you can go to loss levels up to 80% in one of the arms. If you have a large enough R, this optimal value is going to come closer and closer to phi equal to pi by 4, and you are going to reach closer and closer to your limit of eta equal to 1/5. So just a few plots to show the same. So now just in this plot, I choose a fixed value of eta. So just to show how the value of the squeezing angle can help you enhance your phase sensitivity. So eta square is 0.5, r is equal to 5. And on the y-axis, you have the phase sensitivity. On the x-axis, you have sort of the average number of photons that you give is as the input. So you see the yellow line is the short noise limit. So every time you are below this, you are beating it. The Heisenberg limit is going to be somewhere closer to in this sort of white region of the curve. It's much lower because you obviously have noise. So you're not going to reach the Heisenberg limit, but it still beats the short noise limit. And the blue curve is for phi equal to 0, and the red curve is for value close to pi by 4, which is 0.68 or so in radians. So you already see that sort of you enhance the phase sensitivity for any number of photons. So this always gives you a benefit. And then finally, if you sort of want to look at the critical eta, the best you can do, or the worst noise that you can be working against, then you see that on the x-axis I have here eta square, which is the loss in the target arm, and here I have the phase sensitivity ratio. For phi equal to 0, you see that this intersects the on the legend I have a sort of misprint. These two have to be swapped. So the yellow line is for phi equal to pi by 4, the blue is phi equal to 0, and the red one is the short noise limit, so which is 1. So here the intersection is around 1/3, whereas here the intersection is around 1/5, and that's what we sort of expected to have. And these plots essentially have been done for by minimizing the delta phi, by varying all of the parameters that are there in the general expression, θ1, θ2, phi, and so on. And you see that actually phi close to pi by 4 is your sort of optimal setting, under the constraint that the entire theta is such. So yeah, that's more or less that. And then just to conclude, we see that by sort of optimizing the individual angles in the input phases, in the input we can go down to 80% of loss in the target arm, which is nice. And so just for a comparison, in LIGO kind of setups where you have loss in both the arms, this threshold is known to be 50%, which is 3 decibels of loss. So you can do much better for a LIDAR, obviously, because there is loss only in one arm, but nonetheless, it does better. So as we said, phase sensitivity can be enhanced by allowing a more general source parameters. It would be interesting to note the role of entanglement, because although we know that after passing through the beam splitter, it's just two single mode squeeze states and it's no longer entangled, but all the sort of phase sensitivity is maximized exactly where the entanglement is maximized for the sort of theta equal to pi choice. So it would also be interesting to see how the entanglement of the source changes with the sort of input parameters being varied. We could do the same with different quantum sources such as Moon states, cat states, and the others that Dr. Lee also discussed, and also change how you measure it. So instead of the photon number difference, you could also do parity measurements, and that could sort of take you closer to the Heisenberg limit and improve this critical threshold even more. Yeah. So thank you.
All right. Thanks, Stav, for your presentation.
Thank you.
Since we did hit 11:30, I don't want to cut into our lunch break. I think we should move on to the next speaker,
Okay.
who is Jacob Mas